Okay, let's do some practice. Start off easy. Water. Okay, so first step is to add together all the valence electrons. So we have two hydrogens, each has one valence electron, and the one oxygen has 6. So that gives me 8 electrons total. Now, of course, those numbers I got right from the periodic table. Hydrogen has 1 valence electron, oxygen has 6 valence electrons. Next step is to connect all the atoms to a central atom. Now, when you do this, the guiding principle that's almost always going to steer you in the right direction is symmetry. We always want to spread things out as evenly as possible. If you were to put the hydrogen in the center and the oxygen on the end, you can see it would be lopsided. You'd have 2 hydrogens in a row and oxygen on the end. Also remember the Honk rule. The Honk rule tells us that oxygen will have 2 bonds and hydrogen will have 1 bond. Now, as we'll see, there will be exceptions to the Honk rule except for hydrogen. Hydrogen will only have that 1 bond, and that is it. You can kind of think of it like the one-armed element. Hydrogen, if ever you see a Lewis structure, try to build a Lewis structure where you have more than a single dash on the hydrogen. It's going to be incorrect. Now, the oxygen needs to be surrounded by 8 electrons. Currently, it has 2 bonding pairs of electrons, or also referred to as shared pairs of electrons. Now remember, the dash here represents a sharing of electrons. You have a half-filled s orbital from the hydrogen, and you have a half-filled p orbital from the oxygen. And those 2 half-filled orbitals merge together to share electrons to form a covalent bond. Oxygen has 2 half-filled p orbitals, and so it can have 2 bonds, whereas hydrogen only has the 1 half-filled s orbital, so hence it can only have 1 bond. Now, oxygen needs to have 8 electrons around it to obey the octet rule. Currently, it only has 4 electrons, so what we need are 2 more pairs, and these pairs are non-bonding pairs or lone pairs. I prefer that term, lone pair. Lone pair or non-bonding. Now remember, oxygen, if we were to look at the orbital diagram for the valence electrons for oxygen, we would see that we would have the S would be full, and the P, you would have 2 filled orbitals and 2 half-filled orbitals. So here we have our 2 filled orbitals, the 2 electrons, and the 2 half-filled here. Okay, so now we've used a total of 8 electrons, 2, 4, 6, 8. It doesn't matter whether it's a lone pair or shared pairs, it's 8. And so that is the number that we need. Every time you draw your Lewis structure, you need to make sure that every atom is surrounded by 8 electrons except for hydrogen, and that you've used exactly the number of electrons that you came with. Okay, let's try another one. Let's look at ammonia, NH3. So nitrogen has 5 valence electrons. Each of the hydrogens has 1. So again, we have 8 electrons. Connect all the atoms to a central atom. Again, symmetry. And remember, the Honk rule tells us that nitrogen will usually have 3 bonds, which is what we have here. Now I have 2, 4, 6 electrons around the nitrogen. They're all bonding pairs of electrons or shared pairs of electrons. So we need 2 more. And so we'll have 2 or 1 lone pair on the nitrogen. So now we have 2, 4, 6, 8, a total of 8 electrons. This is what we need. And so we now have a completed Lewis structure. Okay, let's try another. Let's try ammonia. I'm sorry, ammonium. Ammonium has a positive 1 charge on it. When I add together all of the electrons, so nitrogen has 5, you have 4 hydrogens, each has 1. Now that's how many electrons we would have if it didn't have a positive 1 charge. But because it has a positive 1 charge, we're going to remove 1 electron, which again gives us 8. Now, when we draw our Lewis structure, we'll see that we're going to violate the Honk rule. We'll have to, because the nitrogen is going to have to bond to all 4 hydrogens. So this is a case where the Honk rule doesn't work, because the Honk rule says nitrogen is going to have 3 bonds, but here we have 4. So there will be exceptions. Don't go to the exceptions unless nothing else works. The Honk rule almost always works, but this is a case where it doesn't. Now, when you have a Lewis structure that has a charge, or you're doing it for an ion, you need to put the entire Lewis structure in brackets and indicate the charge. This enables the reader to quickly, at a glance, see that in order for the Lewis structure to exist, we needed to, in this case, lose 1 electron, hence the positive 1 charge. Okay, let's try another. Let's try carbon tetrachloride. Carbon has 4 valence electrons, and each of the 4 chlorines has 7 valence electrons, so that gives us 32. Connect all the atoms to a central atom. Again, think symmetry, so we're going to have all 4 of the chlorines bond to the carbon. And then, to complete the octet for each of the chlorines, we're going to need to have 3 lone pairs. All 4 of the chlorines. Now the carbon, remember the Honk rule, carbon will have 4 bonds around it, which is what we have here. So carbon has 8 around it, each of the chlorines has 8 around it. Let's double check that we've used the right number of electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've used the right number of electrons, and so this is a correct Lewis structure. Now, so far, things are falling into place pretty easily, but that won't always be the case. Let's look at the sulfite ion. Sulfite ion has a -2 charge on it, so let's add everything up. Sulfur has 6 valence electrons. You have 3 oxygens. Oxygen also has 6 valence electrons. Oxygen and sulfur are in the same family. Now, the -2 charge here means that you have 2 more electrons. Without the -2 charge, you would have 24 electrons, but the -2 means that we have 2 more electrons, which gives us 26. Okay, now when we draw the Lewis structure, we'll have sulfur in the center and then oxygen bonded to it. Again, think symmetry. Now remember, the Honk rule tells us that oxygen is going to have 2 bonds, and we can see that that's not going to be the case here. Again, I'm showing you, at various possibilities. The Honk rule almost always works, but in this case, no. The oxygen can only have 1 bond. Now let's complete the octet around the outer atoms. So always complete the octet on the outer atoms first. And you'll see why in a few minutes. Okay, so now every oxygen is surrounded by 8, and I've used so far 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I have 2 more electrons, which is good because the sulfur right now only has 2, 4, 6 electrons. It needs 2 more. So now I've used the 26, and every atom is surrounded by 8. So what I'm doing here is a really good idea when you do your Lewis structure. Just circle every element and make sure that the count is 8. And then it is an ion, has a -2 charge on it, so like the ammonium before, we need to put it in brackets and indicate the charge. So this tells our reader that this Lewis structure, in order for it to exist, needed 2 more electrons. Okay, let's look at another one. In this one, we're going to have a little bit of a problem. This is carbonate. Now, it looks very similar to sulfite, but carbon is not in the same family. It only has 4 valence electrons. So when I add together all of my electrons, I'm going to have 24 rather than 26. So I'm going to follow the same steps, connect all the atoms to a central atom, carbon in this case, complete the octet on the oxygens here, now, before I put in the dots on the carbon, a couple of things to consider. Remember that carbon should have 4 bonds around it, but it only has 3. And so if I put a pair of electrons here, a lone pair, well, then that wouldn't obey the Hooke rule. And a little bit later in your notes, we'll talk about carbon. Carbon is very special. It's kind of like hydrogen always will have just 1 bond. Carbon will always have 4 bonds. Whereas the Hooke rule here, oxygen, usually has 2 bonds. Here it only has 1 bond. So the other elements, there's a little bit more wiggle room, but not with carbon and hydrogen. They're pretty strict. So in order to have carbon surrounded by 8, I need to bring in what we call a multiple bond, a double or a triple bond. Now, right now, I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons, and that's all that I have, is 24. So I wouldn't even have the electrons if I wanted to put in 2 electrons here or a lone pair here. I couldn't do that because I don't have them. I've run out of electrons. So what I'm going to do, and I'm just doing this for instructional purposes right now. You don't need to do this when you're drawing your Lewis structure. I'm going to take one of the lone pairs off of one of the oxygens, and it doesn't matter which one, and I'm going to turn that into an additional shared pair between the carbon and the oxygen. So let me rewrite that down here. So I have carbon now with a double bonded oxygen, and the others will be single bonded. And then I'll complete the octet on the oxygens. But on the double bonded oxygen, it already has 4 electrons or 2 pairs, so it just needs 2 more lone pairs to complete its octet. So now every atom is surrounded by 8. The oxygen is surrounded by 8, and the carbon is surrounded by 8. So you can see that we haven't lost any electrons or gained any electrons in doing this. We simply made one of the lone pairs an additional shared pair. So now I've used 24 electrons, which is the number that I need to use, and every atom is surrounded by 8. Again, it's an ion with a negative charge, so I'll put it in brackets and indicate the charge. Okay, let's try another. Okay, now let's look at carbon dioxide. So 4 valence electrons for the carbon, 2 oxygens, each have 6, and that gives me 16 electrons to build my molecule. Connecting the oxygens to carbon, and then completing the oxygens octet. Now remember, I'm just following the steps here. So if I seem like I'm going too fast, just kind of go back to the steps that you wrote down. Step 1, add together all of the valence electrons. Step 2, connect all the atoms to a central atom. Again, think symmetry. 3, complete the octet around the outer atoms by adding lone pairs of electrons. And then complete the octet of the central atom. But if you don't have sufficient electrons, then we need to have multiple bonds, which is the case here. We've already used up 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. So I have no more electrons to put any dots around carbon, and carbon only will have 4 bonds anyway, so we know that that's not going to work. So, like carbonate that we just did, I'm going to take one of the lone pairs on the oxygen and make it be an additional shared pair between it and carbon. And I'm going to do that the same to the other oxygen, which gives me carbon with 2 double bonded oxygens. Completing the oxygens octet. And there you have it. Every atom is surrounded by 8, and I've used exactly the right number of electrons, 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So that's the name of the game. Play around with the bonding however you might need to so that you've used exactly the number of electrons that you came with. Okay, now, let's look at something that might throw you off a little bit. This is hypochlorous acid, HClO, and this is the way it's typically written. If we add together all of the electrons, hydrogen has 1, chlorine has 7, oxygen has 6, that would give me 14. Now when you go to draw the structure, you would think that chlorine would be in the center. It's the way it's drawn here. But remember the honk rule, and this is where the honk rule really is quite handy. If you have a couple of choices on how to do something, always follow the honk rule. Chlorine is a halogen. It will have one bond, almost always just has one bond, whereas oxygen will almost always have 2 bonds. So rather than writing it so that chlorine is in the center, I'm going to draw it with oxygen in the center, even though the formula is a bit misleading. So oxygen is going to be in the center, and then chlorine, and then hydrogen. Both. So now, remember the honk rule, hydrogen or halogens will have 1 bond, and oxygen will have 2 bonds, and then they complete the octet. On the oxygen, oops, I should have done the octet on the chlorine first. So now I've used 14 electrons, 2, 4, 6, 8, 10, 12, 14, and every element obeys the octet rule except for hydrogen, and we've also obeyed the honk rule. Now you could draw the Lewis structure with the chlorine in the center, but that's not the way it is. Chlorine only has 1 half-filled p orbital, whereas oxygen has 2 half-filled p orbitals. Okay. Let me try hydrocyanic acid. You'll learn the names of these acids later on. Actually, it's something you learned last year you may have forgotten. Okay, now for this, hydrogen has 1 valence electron, carbon 4, nitrogen 5, so that gives me 10 electrons. So I'm going to bond the hydrogen and to the carbon and the nitrogen. Now to complete the octet on the nitrogen, and this, again, I'm going to have a problem here, so this will be revised in a second. If I complete the octet around nitrogen, that would give me 2, 4, 6, 8, 10. And so the nitrogen is good, the hydrogen is good, the carbon not so much. Carbon needs to have 8 electrons around it as well. So in this case, I'm going to take 2 of the lone pairs on the nitrogen and make them additional pairs between it and the carbon. So this means that that carbon and nitrogen are going to have triple bonds between them. Okay, so now I've used 2, 4, 6, 8, 10 electrons, and every atom except hydrogen is surrounded by 8. Carbon has 4 bonding pairs, nitrogen has 3, and 1 lone pair. Nonetheless, each has 8 around it. Okay, now also add to your notes that only 3 elements can triple bond. Only 3 elements can triple bond. And they are carbon, nitrogen, and oxygen. So as far as triple bonds go, those are the only 3 that are capable. Why? Well, if you look on the periodic table, those are in period 2, and they're very small. So the electrons, the orbitals, can literally wrap around the nucleus in order to form those bonds. But when you go down to higher periods, you have bigger elements and the orbitals aren't able to wrap around. It's kind of like you can wrap your arms around a small tree, but if it's a big tree, you're not going to be able to wrap your arms around it. So triple bonds are limited to relatively small elements, specifically these three. As far as double bonds, many elements can double bond. Even the halogens can double bond, but you're not going to see that for a while. Okay,